The purpose of this video is to serve as a reminder of gravitational potential energy so that hopefully when we talk about electrical potential energy you have a pretty good context in which to put it. So we're going to start off with just the force equation for gravity, and that's just the opposite of big G, which is the universal gravitational constant, times the mass of one object times the mass of the other object, divided by r squared times r hat. And this should look remarkably similar to Coulomb's law, with just a couple of differences, namely the negative sign here and the fact that we're dealing with masses rather than charges. Now what we can do with this is we can take the force of gravity and we can divide it by one of the masses. And to give you sort of a context for this, let's say that this one here is a ball, right? So we have a ball here, and this is the mass of some sort of a central body. So if we go to an example over here, let's say that this is on the Earth, right? So this is the Earth down in here. So that's going to be our big M, and then this would be our little m right here. And I don't know what the mass of this little m is, but one of the things that does occur, and hopefully you remember from last year, is that the acceleration of this little mass m, this ball, will be the same regardless of the mass of the ball. Now, a larger mass, so if this is bigger, then I'm going to give a bigger force out. So I've got a bigger force here, but I also have a bigger mass that I'm dividing it by, and that gives me the same gravitational acceleration. Now here's where things start to diverge a little bit. I can actually rethink this completely. So previously we had said G is meters per second squared. And that's all well and good, right? But there's more to it than that. This G is actually, or at least it can be written as newtons per kilogram. And these are the same thing, but this first one indicates an acceleration, and this one is indicating the gravitational field. And so what I've drawn over here is the gravitational field vectors. So this is a field of vectors showing the gravitational field strength at each of these points. And what that means is that regardless of what mass I put here, maybe this is 1 kilogram, 2 kilograms, 3 kilograms, whatever, the gravitational field strength caused by the Earth will be the same at this point no matter what object is there. And that's what that equation is saying. And this is just how I can rewrite it to make it a little bit more concise. Now, one of the reasons that we can do this, that we can treat it this way, is that mass is the property of a body that's responsive to gravitational interactions. That's why it's here. Okay? So it's this property of a body that's responsive to gravitational interactions. And you might be thinking, in the past, I've described mass as a measure of a body's inertia, right? Resistance to changes in motion. And it turns out that mass is this, and mass is also this. And if we look at sum of forces equals m times a, this mass is the inertial mass, the measure of the inertia. If gravity is the only force acting, then this mass is the gravitational mass. And it just so happens, though, that these two masses are exactly the same thing. And so they cancel out and give us this sort of a dual purpose of G, meaning the acceleration caused by the gravitational force, and G as in the gravitational field strength. And I will say that actually makes electrical potential energy, I think, actually simpler, because there's no confusion at this level of these two different concepts being the same exact value all the time. So as far as the gravitational potential energy goes, it's just the opposite of the amount of work that's done, which we can find by just taking the opposite of the force of gravity times the distance through which it moves. And if we go over and look at this ball example here, so let's say that the ball falls from h naught to h final. In doing so, our r vector is downwards and our force vector is downwards. So when we do the dot product, we actually get a positive result there. So gravity is doing positive work on the ball. However, because gravity is doing positive work on the ball, it is no longer able to do as much work to the ball. So it's lost gravitational potential energy. So this has gone down, even though the work was positive that was being done. And we can do a further substitution. This is the case. Well, actually, this is always going to be the case. When you have a relatively constant g, though, when we make this assumption that g is constant, then every little increment of distance through which the ball drops, assuming that these increments are equal in size, this is a certain negative change, and this is the same negative change, and so on. So these are all equally sized changes. So I can just say that the change in the gravitational potential energy equals the opposite of m, g dot r, if g is constant. If g is not constant, then this would only give us a rough approximation. This coming year, we'll actually go into how to solve it when it's not constant in a way that's better than doing a rough approximation. But for now, this is going to be good enough. We'll just assume that it's constant at this point and focus on getting the idea right rather than getting all of the math right now. So hopefully this makes sense. Change in gravitational potential energy is just the opposite of the work done by gravity. And hopefully this formulation of gravitational field strength and gravitational force mesh with what you're seeing in terms of the change in the gravitational potential energy.